In the last segment, we took a look at the idea of the shape factor, and what we're going to do in this segment is we're going to solve an example problem involving the shape factor. So if you recall, the shape factor is kind of a quick way of being able to compute conduction in a problem that cannot be approximated as only being one-dimensional. So it'd be for two-dimensional problems. And so what I'll do, I'll begin by writing out the problem statement, and then we'll work through towards a solution. Okay, so there's our problem statement, kind of a long one, but what we have the hole is drilled through the center of a solid block of square cross-section, and the dimensions of the square cross-section we're told are 1 meter by 1 meter on a side. The hole is drilled along the length, so the length of this square cross-section is 2 meters long. And we're told that a warm fluid passing through the hole maintains the inner surface at T1 equals 75 degrees C. So a very simplified approximation for convective heat transfer due to the fluid. And as a result, what we'll do is we'll assume the inner wall temperature of this hole is at 75 degrees C. And the other thing we can assume is the outer block temperature is at 25 degrees C, and then we want to find the heat transfer. So let's go through the steps that we do for all the problems. We begin with what we know, and then we'll draw a schematic and work through the assumptions. So our known items are okay. So that's what is known and what we're looking for. Let's draw out a schematic, and that will help visualize what is going on in this problem. Okay, so there is the schematic for our problem. We have a block. It is dimensions W by W and length L, inner temperature T1 and the outer temperature T2. And so when you look at this, it becomes quite apparent that we cannot assume this to be one-dimensional conduction, as we were able to do when we looked at thermal resistances, where we could have a pipe, a very poor-looking pipe. But if you recall, when we had thermal resistances, we could assume that the conduction was in one dimension, basically going in the radial direction. Here, given the fact that we have a square geometry around a circle, we're going to have edge effects going on, and consequently this becomes a two-dimensional conduction problem, and that's why we have to go to the shape factor in order to solve it. So let's take a look at the assumptions, and then we'll work through the theory, basically using the shape factor. Okay, so we're assuming this is happening in steady state and that we have 2D conduction. And the other thing that we're assuming is that the ends of the block are well insulated, because if we look at the schematic again, we have something like this, and this is 1 meter, that's 1 meter, and this is 2 meters. So the block is really not that much longer than it is wide. And consequently, in order to ensure that we do not have conduction going in the axial direction, what we'll assume is that the edges of the block are well insulated, preventing any kind of heat transfer going in that direction. And consequently, we're assuming that all of the heat transfer is going in this direction. Well, it's two directions because we have two dimensions that we're looking at. But then we'll have edge effects, the fact that we have these corners here, which I just mentioned. Okay, so analysis. How are we going to solve this? What we're going to do, we're going to use the shape factor. So you have to find a table that has a shape factor with this object in it. That's usually step one for solving these problems. And I just happen to have a table that has this value in it. So we look up the conduction shape factor. And this is for a cylinder centered in a square of length L. And for that, the shape factor we're told is the following. Okay, so we're given that R would be half of the diameter of the hole within the object. It's interesting to look at this because we have the natural logarithm in the denominator, and that was what we found when we looked at conduction through a pipe. We always found the natural logarithm in the denominator. But anyways, when we put in the values, we know all of the dimensions here, so we can determine this. And we get 8.588 meters is the value for the shape factor. And then it's a pretty straightforward and simple calculation with the shape factor. Really the biggest trick is to ensure that you have that shape factor for the shape that you're looking at. And then we plug in the values. We know the shape factor, so we can do that. Thermal conductivity was given, and then the temperature difference, it was 75 on the inside and 25 on the outer wall. And with that, we can then evaluate this, and that tells us that the heat loss for this particular object turns out to be 64.4 kilowatts. So that is an application of the shape factor, and it enables us to solve in kind of a quick and efficient manner problems that involve two-dimensional conduction. But again, the biggest trick is to ensure that you have a shape factor for the particular shape or configuration that you're looking at. And one thing to say is that shape factors only exist for a limited number of scenarios. Okay, so what we can say is that shape factors only work for a limited number of scenarios. You need to have a shape factor for it. So if we have a problem and we cannot assume it to be 1D and there are no shape factors, then what happens is you end up going to numerical methods. And so that's where we're going in the next couple of lectures. We're going to be taking a look at two-dimensional conduction problems using numerical solutions. And we'll see the power of numerical solutions. It's not as quick as you would get with hand calculations like what we've been doing thus far, but it does prove to be a very efficient method, especially for heat transfer, being able to calculate temperature distribution in objects. And what we're going to find is the biggest challenge with numerical methods is going to be estimating the boundary conditions. So what goes on in the solid is pretty easy, but what's happening on the surface is usually the biggest challenge. But that's where we're going in the course. We're moving into numerical methods for two-dimensional conduction.